I'm going to discuss part 2 of two-dimensional geometric transformations. This is our lesson number 5. And first, let's try to understand composite transformation. Now we have a point P. Then to P we apply P1 P. Actually, this is a transformation matrix. Okay, then after applying that particular matrix, this point comes to the position P1. Then again, to P1 we apply another matrix, another transformation matrix, that is T2. Then we get point P2. Okay, so P2 after applying T2. Okay, then again now likewise we have we get then P n T n into P n minus 1. Now in this way we apply these matrices and we get Pn minus 1, then we get Pn by applying the matrix Tn. Okay, so now here we have applied n number of transformation matrices, and P initial position and the final position of P. This is the initial position. This is the final position. So we have to apply T1, then find P1, then apply T2, find P2. Likewise, then in the last step we apply Tn to Pn minus 1 and we get the position of Pn. Okay, so this one now composite transformation means, now let's see here. Here we P1 we replace, here P1 we replace from this one. Okay, then we get P Pt1, this one into T2, that is P2. Okay, likewise if you continue, then we can get Pn. In the same way we continue with downwards, you will get Pn here, Tn, T2, T1 into P. Okay, so now we can compute this one. We can multiply this chain of matrices and compute that value. Let's say that is T. Okay, this value T is called the composite transformation matrix. In other words, we can get the coordinates of the Pn simply by T into simply multiplying T by T and P. Okay, T and P. Okay, so therefore we do not have to compute P1, P2, likewise up to Pn minus 1. Okay, we do not have to compute those values. What we have to do is we have to compute this matrix, and we can directly compute the coordinates of P1 just by multiplying T and P. So this is how we should find the value of T. Okay, that is the idea of composite transformation. So this is very useful. Okay, then let's see how we can apply this one. First one, transformation matrix for general pivot point scaling. That means now in our lesson number 4, we have studied Tx, Ty, a matrix, transformation matrix for translation. Okay, then for scaling we have studied this one. For rotation we have studied this one. Okay, translation, that is okay. That is simply we have a particular point, then Tx amount along the x direction, x axis, direction of x axis, and Ty amount along the direction, positive direction of y axis, and then we get the new position after applying this matrix. Okay, that is okay, but when we consider these two transformation matrices, we have scaled. Actually here in scaling what happens is we have x comma y, that is the initial coordinates. When we apply this matrix, then you will get simple x into x comma simple sy into y. This is the coordinates of our new point. Okay, here what we have done is we have multiplied the point coordinates of x coordinate from sx and y coordinate from sy. Okay, and let's see this one. Here when we derive the transformation matrix, we have derived it so that the point rotates around the origin. point rotates around the origin in anti-clockwise direction by an angle of theta. This is the new position theta. Okay, rotates around the origin. Now we are going to apply the concept of composite transformation. In order to get scaling, now here scaling also, what we have done is we have a particular point, then with respect to origin, okay, we scale with respect to origin. Rotation also we perform with respect to origin, okay. So if we want to scale and rotate, for an example, scaling, if we want to perform it with respect to a point somewhere here, okay, and also we want to rotate the point around this point by an angle of theta. Okay, this is the new position. Now this is our pivot point. In order to do that, we need composite transformations. Okay, so now let's try to understand. Here we have our pivot point. The coordinates of the pivot point is x1 comma y1, and now we have a point. This is the point of our interest. We want to scale this point with respect to this pivot point. Okay, so that's what we have to do. So in order to do that, we want to find the composite transformation matrix. First, what we should do, we first first move this point to the origin. That means, in other words, we consider origin is here. Okay, that means t. In order to do that, here we have to minus x1 and have to do this one. Okay, and now now we take the origin to here. Then we can perform scaling with respect to origin. Now again we move to its yes, I will try to explain this again. Now this matrix, the purpose of this matrix, is to scale with respect to the origin, okay, but we have to scale with respect to this pivot point. Therefore, first what we do is we take the origin to this position. In order to do that, we have to um, translate the origin to here, and after that we scale with respect to origin. Now again, to get it to the actual position, we again translate origin to here. Okay, that's what we have done. Now if we perform multiplication, now here a 3 by 3 matrix, here also we have 3 by 3, here also we have 3 by 3 matrix. This one 1 0, now x1, okay, 0 1 y1, 0 0 1. Here sx 0 0 0 sy 0 0 0 1. Now here 1 0 minus x1, 0 1 minus y1, 0 0 1. Okay, now one 0 x1, 0 1 y1, 0 0 1. Now let's multiply these two matrices and put here. This one is Sx, okay, Sx into S1, Sx 0 0, this one 0 0 0. Then here minus yes, minus x1 Sx 0 into this one 0 0, okay. Now you get this value 0 0 0 0 sy 0 sy 0. Then 0 minus y1 to sy 0 0 minus y1 to s1 sy 0, okay. Then here see 0 0 0, this one 0 0 0 0 0 1, okay. Then you get this one, and now here you get then Sx, then here 0 0 0, Here we have 0, 1 into, yes, this one, x1 is x, okay, see 0 into this plus x1, then 0, 0, 0. Here we have 0, then here we have 0, sy, 0, therefore sy here. Now 0 minus y1 minus y1 sy plus y1. Then here 0, 0, 0, all zeros we have here. Then 0, 0, 0, 0, 0, 1. Okay, now our matrix T Sx 0, 1 minus Sx x1, 0 sy, 1 minus sy y1. Then here we have 0, 0, 1. Now this is our composite transformation matrix. That means if we apply, if let's say if we apply this matrix, now if our point is P, okay, so to P we apply T, then we will get, from this we will get coordinates of a point when we scale this point with respect to this point using these two factors. Okay, that is the meaning of pivot point scaling. Okay. Then let's discuss transformation matrix for general pivot point rotation. That means now x, y. Now if you could not understand the previous one, that means previous one means transformation matrix for general pivot point scaling. Now in this example you can understand very clearly. Now you know what you have learned in lesson 4. The transformation matrix, this one. Here theta means, if you apply this transformation matrix to a point P, that means with respect to origin it rotates an angle of theta in anticlockwise direction. Okay, this is the position. Okay, so here our we rotate around the origin. Now let's say here what we need is we have a point x1 comma y1, and now we have a point x comma y. This point we want to rotate around this one by an angle of theta. We have to find this one, okay, coordinates of this point. So in order to do that, what is the composite transformation matrix? In order to do that one also, first what we have to do, we have to get the origin here first. So in order to do that, we translate x1 y1. Okay, now now we rotate around the origin. That means, in other words, now we have we get this point here, now something like that. Now our new point is here, this point is now here. Okay, we rotate the point now around the origin by an angle of theta. Okay, then after that, now we again translate to the actual position, and then you will get this point. So t x1 y1. Okay, so in that way we can get the composite transformation matrix. Now let's try to compute this this one 1 0 minus 1 0 1 minus y1 minus x1 minus y1 0 0 1. Okay, that is the matrix. And now here cos theta minus sin theta 0. Okay, sin theta cos theta 0 0 0 1. This one 1 0 x1 0 1 y1 0 0 1. Now we get this matrix 1 0 x1 0 1 y1 0 0 1. This one cos theta 0 0, and next one 0 minus sin theta minus x1 cos theta plus y1 sin theta. Okay, now here sin theta 0 0, sin theta, this one cos theta minus x1 sin theta minus y1 cos theta minus y1 cos theta, and 0 here 0 0 0, all zeros, 0 0 0, all zeros, 0 0, here 1, here we have 1. Now let's multiply these two matrices. Now multiplying these two, we have got this one. Okay, so now T means here here we get 1 into cos theta 0 0 cos theta 1 into minus sin theta 0 0 minus sin theta. Then here we have this one minus x 1 cos theta plus y1 sin theta plus x1. Okay, then here 0, here sin theta 0, here we have cos theta 0, then minus x 1 sin theta minus y1 cos theta plus y1, this one 0 0 1. Okay, now we can simplify it. See, cos theta minus sin theta. Okay, then yes, that's all. No, that's all. No need to you get this one. Okay, minus x1 cos theta plus y1 sin theta plus x1 minus x1 sin theta minus y1 cos theta plus y1 cos theta minus sin theta cos theta. Yes, you get this. Now the problem is not how you compute the transformation matrix. If you are familiar with matrix multiplication, this one is very easy, but the logic is the important one. So I will again explain. Now we have xy origin. Now r theta means if we have a particular, if you have a pivot point, okay, pivot point, and coordinates of this one is x1 comma y1, and we have another point xy. We want to rotate around this point by an angle of theta. Okay, and we have to find this one. So in order to do that, what we should do is we know how to rotate around the origin. Then what we should do is we first translate to the origin. That's what we did like this. Okay, now our point is here. Now we compute when we translate Okay, when we perform this part, now this point is here, this one is here. Now our new point is our this point, it is here now, this one is now here. Okay, so now we apply r theta, that means it rotates, and we have computed this point. Again, in order to get this one, what we should do, again we retranslate using x1 and y1. That is the logic here. That is how we compute the transformation matrix. If this is our point P, this is P, okay, this is P, then TP will provide us the coordinates of this point. Okay, that is the logic behind this uh, transformation matrix for general pivot point rotation. And scaling also, you can think it in the same way. Now we have a point. Now this is our point of interest. Okay, this is our point P. And now we know this one Sx, Sy. This one actually, this one, if we apply this one to a particular point, if we apply it to this, that means novel coordinates will be x into Sx and y into Sy. X coordinate will be this one and y coordinate will be this one. Okay, we say this one will scale with respect to the origin, but if we want to scale with respect to a pivot point, what we should do, first we have to translate. Okay, now our new point comes here. Now our this point come to here. Okay, then this point will be somewhere here. Okay, this one will be somewhere here. Now we perform scaling with respect to the origin, and now again we have to retranslate in this way. Now if you compare this with the rotation example, then you can understand this one. Okay, so this is the composite transformation matrix. If we apply T to P, then we get the coordinates of the point with respect to this pivot point. Okay, and that's the end of this lesson. Thank you for listening.